Picking up from the last video, here's one of the Stanton drives. You can see nice four-wheel pickup on the bottom. You can see the can motor here in the center going out to a worm gear on each side, and then each of the individual axle gears. So when you pop 6 screws out, 2 here in the center and then the 4 on the ends, the bottom plate will drop out and we're left with this. So the motor alone, I'm spinning right now, as you can see. Just kind of breaking in at 6 volts, and we're pulling 45, 46 milliamps. So this motor is marked as a 20 by 32, so that would be 20 by 32 millimeters. That's a pretty typical size for an HO locomotive. So they're using that in an O-scale locomotive. Just to give you some comparison, this would be one of the cheap Micromark motors, 86546. And we can open that up and show you. So this would be what people might use for repowering an HO locomotive. It's somewhat comparable. You know, we don't know exactly what that motor is. The Northwest Short Line, it could be a Sagami, because they often use Sagamis, but it's not badged for that. But just for comparison's sake, if you wanted to see, we could fire up the Micromark here, which has a somewhat similar RPM per volt, maybe a bit lower. At a minimum, that would give you a noise kind of comparison. Same voltage, a little less current, actually a lot less current there. 13 milliamps. But a smaller motor. Could be used as a replacement though. In fact, it's so small you could even put a flywheel on each side if you used a motor like that. Alternatively, Micromark does sell a little larger motor. They're 86529. Compared with the previous one, you can still see, you know, it's a flat can motor, but specs out a little bigger, and it's in fact larger than the Northwest Short Line motor. So to place this in the housing would require some modification. It's a much lower RPM at 12 volts. Pulls about the same, but more amperage in the smaller Micromark motor. It's definitely noisier. And lastly, just for comparison's sake, I have a high quality motor here from A-Line, Protopower West. This would be one of the old premium Mishima motors. Comparable to the larger Micromark in size. So would not be a drop-in replacement for a Stanton drive. But just to show you kind of ballpark motors in the vicinity for these kinds of applications. That would be kind of cream of the crop for an HO application. What are we pulling there? Oh, 20 milliamps. A lot of torque though in that, and a bit lower speed too. back over here to northwest short line. There we go. Settling in. 45. Maybe I'll hop up at 46. Okay. So that motor sits down in the upper lid, which is the cradle for it. So to show you that small micro mark, you know, it definitely would fit in there. And in fact, even with a little room to spare, and we have to trim down the axles, and there would even be room for flywheels. But it might not perform as well as what is likely a Sagami in there. The high performance Mishima, not going to work. It's just too wide. So something like this would require some modification, a lot of dremeling in there. Could be done though. There wouldn't be much left to the center sides of this housing in order to get that to nestle down in there. So we'd lose some structural integrity. But anyways, that's kind of what we're starting with, and some other things out there in the market which could be candidates if for whatever reason you needed or wanted to replace that motor with something different. So let me turn him off so we're not listening to that buzz away. So let's get on to the housing. Here's what I learned there. It's very novel. The wheel sets here are captured in these bronze bushings, and I can raise one out here. The real novel part is how the axle is drilled through the bronze bushing is off center. So you can see this one's biased to the left and that one's biased over to the right. And that's kind of cool because if I just move one of those axles around, swap it around backwards, I've now changed the wheelbase. So that's neat. As far as performance, you know, what you would want to have happen is while these wheels are in here and without the motor or anything, they should spin, you know, very freely. And as you can see, that one for the most part is. They were not when they were brand new, much to my surprise. And I didn't really realize that until I had taken it apart to this stage. But they are right now. There's very, very little drag on them. Here's the issue. So these bronze bushings fit down in this injection molded lid into these slots. And being injection molded, these captured slots, which are going to let that bushing move in one axis in and out, have some draft angle to them. So the farther the bushing goes down in, the tighter it's going to get. I took some measurements here, you know, for that. The issue is if you look at these bronze bushings up close, you know, they've got very crisp corners on them. At least they had crisp edges and corners on them. And you cannot make a crisp inside corner injection molded part. So there was some binding of these bushings going down into those openings. And in order to fix that, you know, essentially what had to be done is each, just using a small jeweler's file here, each of the edges had to be broken over with a file. So, you know, 1, 2, 3, 4 going around that way, and then 1, 2, 3, 4 on the inner sides of the face, and 1, 2, 3, 4 on the outer sides of the face, as well as each of the corners like this. And these have all been done. You can see that these have nicely broken over edges. And once that was done, you know, not changing any, not filing on any of the faces, but just filing on the edges and the corners. Now the axle will slip down, very nicely into the Delrin housing without binding. Just have to align it, and then in we go. And the axles will spin very freely within there, whereas before there was a lot of drag on them. So I think that's a necessary finishing step. Now I had cleaned off a lot of the oil to make it easier to handle these during the filing. So the last step after filing and blowing off any shavings was to go in and re-oil them. I didn't use anything fancy, but just the Labelle, 108, put a shot on both sides and kind of work things around, that way. And that was, I can feel that. That's a major improvement there in the drag and the axles. The second thing, which was, I think, equally severe of a problem, was down in there are the adjustment screws. See if I can get the light on it right here. I'm going to pull out the wrench here. Interestingly, these are metric. I had to use a 1.5 millimeter Allen wrench. So there's a screw there, and there's a screw there, which you would adjust from the top right here. So those two screws are going to change the clearance of the teeth, between the axle teeth here and the worm gear on the motor, changing the clearance of engagement between the two, which is going to affect a lot of things: gear wear, noise, how smooth everything is running. The issue is that these two bushings need to be vertically aligned equal. So if you make a change to one of those adjustment screws on one side, the same adjustment needs to be made to the other screw on the other side. And when I was disassembling my trucks, they weren't necessarily all equal. The problem with that is as soon as you would get one of those screws higher than the other, because those bushings are captured in those slots, they can only move vertically. And so once things get off just a tiny little bit, you're going to get binding in the axle very quickly. So what I did is I backed off the screws entirely and then dropped in, one axle, one wheel pair, all the way in. And then by feel, tightened up until I just get a little bit of resistance, knowing now that, okay, there we go. I can feel that's just touching the top of the brass bushing, and that one is too, right there. Okay, so we're now kind of set level and at the beginning of the stroke on in, and then we do the same thing with the other side. Then reassemble the truck. And any adjustment that's made on the tooth clearance beyond that to one side on one axle, like let's say I turn this one, half of a turn in, this one needs to be turned in half a turn in as well. Got to count and match turns on both of those so that the entire axle is moving down or up at the same distance on the right and the left side to minimize binding. So I did that with this one when I put it all back together, and it should be running much more freely now. But the proof is in the pudding, as they say. So let's put everything else back together and we'll test it out. All right, I'll put back together. We can apply the same 6 volts that we had before. No load. Very nice. Seeing about the same current draw as we were before. Put a little load on it. Slow it down. Looks good. I think we had a positive impact on that. There's binding. You can hear it. Okay, so at this point we can put the truck side frames back on. Okay, there we go. And we can put our test chassis back on. Much slower and much quieter. Lower voltage, I think lower amperage too. Once I got it down to 1.5 volts, our last 2 lap times were almost 1.5 minutes. And I'm able to keep the voltage the same both directions. So this looks pretty good. This is about as good as I think we're going to get analog. We can take a look at the results, tallied after a few runs here. But, you know, I think those 3 things running in the motor as well as breaking all the edges and corners on the bushings and adjusting the set screws all together kind of added up to having a good improvement. Maybe the re-oiling helped too. You know, it's not ever going to be as good as something with a large can motor and a flywheel. But this is pretty respectable for what it is. It's definitely hanging now. Some of the other stuff. So the next step is we'll take a look at what we can do with the decoder, get in the digital realm and see if we can get even more performance out of it. But I think this is the best that we're going to do with analog. This would be at 6 volts. Much quieter. That would be up to 9 volts.